done distributed systems. You now just want to see what is the trend, what is now out there. You've talked about objects, you've looked at services, you've looked at databases, you've looked at web. All these, you have really looked at all these things within your 4 years of study. So here, this is just an extension. So on completion of this course, we are expected to at least be able to program in C#. Then after programming in C#, we can apply threading and networking, which is not a new concept. We have concept of now the clients and servers. Then you're also going to look at some XML concepts. So you're going to look at web servers. Then we see where XML comes in. Within XML, we now see how to write XML. We see what is WSQL, the description language, how does it work, etc. So it's more of everything that you already know. We also now just after that XML, we look at this objects, how to create the objects, which I'm sure you have done most of this in Java. So we are just going to now look at most of these things and now change it and do it now in C#. Then apart from that, we are going to now see web services. With the web services, we can use the SOAP. So we're going to see SOAP, how it works. Then we can look at the RESTful services and see how they work. So this is just an overview of what we are expected to look at in this particular course. Then apart from that, it's expected that exam 50% and continuous assessment 50%, but we're going to look at how it goes. We can change it to 60, 40, depending on how the semester goes. Sometimes the semester can have the coursework, then it becomes too difficult for some people and they request that you have more weight in the exam, etc. So you're going to see, but we're supposed to have a 50, 50, but that can change. Then mode of delivery, we are going to just have the discussions. The lectures will be more of discussion because we already know these things. Then we are going to be reviewing papers. So I'll be giving you a paper, you go and read and you summarize. So that will assist in better understanding of the concepts that you already know, because they are not new concepts. So the best way to actually understand them better will be reviewing papers. Then we'll also have practical assignments. So like things like the C#, we are not going to sit down again and start asking ourselves what is a variable, what is a function, etc. We're not going to do that. Things like C#, we already know how to code. So it is just an assignment that I'm going to give you. Then you just go and now find out what's the syntax in C#, then you just do the assignment. So since we're in 4th year, we will not do like the way we do in 1st year, where we are sitting down to do everything because we already know. So papers will be more of what you're going to do and assignments. Lectures will be there and the tutorials, but it will be more of a discussion and adding to what we already know. So with that, we need somebody whom we can be contacting, somebody like a module leader or a class representative who we can contact, such that with that particular person, if there is anything, they can actually call me or write an email on behalf of everyone. So do we have a volunteer or do we have somebody that who already does that? Do you have someone who really does that? And write something in the chat. You really have somebody who does that? Or any volunteer? Okay. So with time, you can now tell me who you want or who can volunteer to do that. If there will be no one, we can just communicate through. Oh, I already have two volunteers. So there's Jerry for Group B. Thank you very much, Jerry. Then Caesar. Caesar, in which group? Also, Caesar is in Group B. So I can be talking to both Jerry and Caesar. So thank you very much. Jerry and Caesar, kindly just write a small email. So you can just write an email to just tell me that you are the representatives. It's easy when we have a representative because for communication purposes. Because sometimes if maybe all 50 of you write an email, I might not be able to read all the emails. So if I just have one person writing the email, then when I see that they're writing I see their email, I'll know they're representing everyone and I'll be quick to respond. So thank you very much, Jerry and Caesar. So next thing, I wanted to share the paper that we will review for the first paper that we want to review. So this paper will more of introduce us to the course. It will now tell us, it will assist us to understand more on what we are looking at so that I will not be presenting ideas and you just taking in ideas. Sometimes I might be lying to you and you taking everything. That's not what you want. You want to be able to collaborate so that both of us can assist each other. So one of the things I want us to do, I'll share this particular PDF document with both Jerry and Caesar. Then they can forward it to you. Then before we continue, do you prefer using Google Classrooms or the e-learning sites? Which one do you prefer? For posting of notes and any materials, do we prefer Google Classrooms or e-learning? There are two. E-learning. E-learning. So the e-learnings are minis. So okay, two classrooms. The rest are e-learning. E-learning. Okay. So I think e-learning has more votes. So I'm going to ask the course administrator to create for me an e-learning page because now I can't create it from my end. So she'll have to create it for me. Once she creates, I'm going to also send the details to both Caesar and Jerry such that we can now access everything. And also the communication and everything, we can have both email and e-learning. So in this particular paper, it's more of introducing us to the web services. So it's more of talking about the history. When did it all begin? How did we get to web services? So here you're going to look at World Wide Web. So it's going to just introduce you to World Wide Web and how it started. So after World Wide Web, then there arose the need to have business to customer solutions. So there is the B2C solutions. After B2C solutions, then we have now enterprise. There was the enterprise technologies that now came about. Then there was the business to business solutions. Then service oriented architecture. Right now, we are more of moving our legacy systems to having service oriented architecture. So most systems are now trying to be able to be written as a service oriented architecture. And one of the things that is being written as a service oriented architecture, now using this service oriented architecture, is the web services. So web services is just one of the things that is using service oriented architecture. But also most legacy systems are actually moving towards the service oriented architecture. So I'd like us to just read this paper. So the first assignment is to read this paper and summarize. I will put a link in the e-learning site whereby you will submit your summary. So what, because it's a very It has 40 pages, but now it has, I think, a spacing of 2, so it's very short. So if you compress it, it's less. So I want us to read this and review this so that we understand what is happening. So we understand now with the distributed, also with the distributed systems. We want to get the brief history of distributed computing because we have done something in distributed systems. So it's just a recap, the history of distributed computing, whereby if you really look at it, the first thing before even distributed computing, we had the mainframes. So you had the mainframes, which we usually access the mainframes is just a dumb terminal. So with a dumb terminal, because the terminal did not have anything to do with it other than just access the mainframe computer. So we just had a dumb, it was more of a conduit, like you can have a conduit pipe. So it was just an access to the mainframe. Then, of course, with time, we now had the PCs. So we are using now the PCs to access the mainframe computer. So after the PCs, which are now accessing the mainframe computers, then we had now the architectures. So we had now the 3-tier architectures where we have your server, you have your application server, and you have now the PCs. Now with the PCs, they now have a browser. So from the 3-tier architecture, we went on to the n-tier architecture. So with the n-tier or entire architecture, then you can now see where the distributed systems were actually coming in. So that's what we want. One of the things we also looked at with distributed, what can actually be distributed? I have just been talking about distributing. What can we distribute? What can be distributed? Distributed, what can be distributed? What are resources? Yes, you can distribute resources. What else can you distribute? Files, you can distribute files, which are also resources. What else can you distribute? The data, that's very good. The services, very good. Computing power, very good. Yes, compute resources, very good. So with the with distributing storage, good. With distributing, you are talking about things that you can distribute. With the storage, anything that you're storing, as you're distributing the storage, that's where you had in the advanced DB, you talked about distributed databases. So within distributed databases, that's where you're talking about now the distributed storage. That's where you're talking about things like the fragmentations, sharding, horizontal sharding, etc. You're talking about more of how can you distribute the storage instead of putting things in one place. How do you distribute the storage? You can see systems, applications can be distributed. That's very correct. Apart from storage, you are also talking about computation. So there's somewhere you talked about how you can distribute your computation. So instead of having a computation task on one computer, you are having that computation task on multiple computers. So you are having a distributed computation. That's where you talked about maybe map reduce. Did you talk about map reduce somewhere? When you're talking about distributed computation, did you talk about distributed computation, map reduce, where you're having, okay, Hadoop is the one which is using map reduce. Then currently we have a Spark, which instead of map reduce, it's now using transform reduce action. We talked something about that. Distributed, when you're distributing computation. Okay, I don't know. Silence means a yes or a no. So no. So I guess I think I don't know where it should fit, so it should be somewhere in one of the units. So if you are looking at computations, at your distributed computations, then you just find the aspect of map and reduce. It's not a very difficult concept. It's just a simple concept, but just so that you can distribute your computation. And also, there was something on messaging you did. Did you do something on messaging? How to communicate and messaging as you're doing with distributed systems? Anything to do with the message passing? Message passing, is it a no? Anything to do with RPC? Interprocess communication, yes. You did something on interprocess, good. So you did something on that. So that's very good. So if you did RPC, then you also introduced to RMI, remote method invocation. That's what you did. So this is what the paper is also all about. So it introduces you to RPC, then RMI. Then after now, RMI was now for the Java. Apart from RMI, you also did something on now callback, common object requests broker architecture. We did something on this. So these are now the distributed computing technologies. Good. So I think we are at a good place. So so that is what we'll summarize. Apart from now the distributed object technology. Now we want to now see, because we have been talking about now the distributed object technologies, which you have talked about the callback, the Java, RMI, etc. But then again, with web services, so apart from that, those ones cannot be used with the web services. So with web services, we now want to use something different. So with web services, we want to now use the service-oriented architecture. So that is what we are now going to learn. We are going to introduce to service-oriented architecture. Somebody wants to say something? So with the service-oriented architecture, it's more of an understanding. You'll have an overview of the architecture, understand how it actually works, because it's also used in cloud computing, etc. So there is now the service-oriented architecture, how things are now made to be services. So you're having more of services. So you're moving from now the legacy systems to now more of services. Then apart from now service-oriented architecture, you're going to see how it's applied in web services. Then as you see how it is applied in web services, that's when you come about with the web service description languages and XML, which we are also going to look at. So we're going to look at what are web services. Then now we now look at the XML and the SOAP. Then once we look at the XML SOAP, then we come and now look at, you can now do your rests. Good. So we're going to look at now the web service standards. So this is just an overview. I'm just taking you through what we are expecting in this unit. So we look at that. So there's a question, is this a broad unit like distributed systems? So, okay, in my opinion, it's more of adding to what you already know about what you already learned in distributed systems. So I can't say it's broad, because once you finish reading this and summarize it, you'll find that you get an overview of what we will do in this unit. That's why I want us to summarize this particular paper. So it's just an overview of what we are going to do in this particular unit. So it will not be broad, because now if you look at maybe one lesson, we're just going to now look at XML. So you just have a whole lesson looking at XML. The next lesson maybe looking at another concept. So you'll find that it will not be that broad because you have already done distributed systems. So it won't be that broad. So this paper I'm going to now send it. That's what we're going to look at. Then the first chapter on my first let's share something else. Okay, there's a question: how long should the summary be? With a summary, have the important things. Summarize the important things. A summary is more of, there's a paper that you have read, what have you understood? So that's what I want. So just summarize for me what you have understood from that particular paper. So I will not tell you the number of pages. I just want you to summarize what you understood from the paper. So today, I was just going to go through what you have already done. So it's more of a discussion, because everything that you have told me that you've done is what I wanted to go through. Just message passing, because I'm looking at now communication, because we have said that we have talked about distributed. You've said if you're looking at distributed widely, there are so many things that will be actually distributed. So here I'm just talking about how does communication happen in a distributed computing environment. So it's a recap. So I'm just looking at before the distributed objects. So I'm looking at message passing. Then I look at now distributed objects. Just look at what are distributed objects. Then we look at now the remote procedure call. This one we have already looked at it, so I'm going to skip it, or we're just going to talk about it. So it's more than that. Then the event-based technology. Then the tuple technology. So when you're looking at message passing as now the development paradigm, so you'll find that it will be more of two or more processes communicating in operating systems. You looked at now inter-process communication. Within inter-process communication, you looked at shared memory, and you also looked at message passing. Is that correct? Is that correct? Or in operating systems? Operating systems class? You have looked at message passing, and you have also looked at shared memory architecture. So you're looking at processes. It's more of how do processes communicate. So processes of how do they communicate? One of the ways they communicate is through message passing. A simple example that I can give is when you're looking at the protocols. In networks, you looked at how protocols are actually communicating by sending of message. If I look at a simple one like HTTP, you looked at how HTTP communicates with the methods get and post. Is that correct? Okay, so we had message passing. So we'll find that two or more processes running in parallel will actually be communicating by sending and receiving messages. So you find that each process is maintaining its own local memory and it's coordinating. So they're coordinating so that they can actually send. So they're more of sending a message and receiving a response. So when you're looking at message passing, an example is when you're looking at TCP/IP. So when you're looking at TCP/IP, there is now the sockets. When you're looking at sockets, where when you're sending a message, then you'll have to include some information. So one of the information that you'll have to include is maybe the IP address. So you want to now know where are you sending it to. So you want to send, then you want to now know which server are you sending it to. So you want the port number, the IP address, etc. So that is a message. So when you're sending a message, when you're using message passing, you're looking at an example, you're looking at the sockets, then you're more of sending a message, then you have to have all this information included in that particular message as you're sending it. Then, of course, also with receiving the message, then also the message has it also has some information that you have to decode. So when it receives the message, it has to know where is the message going to. So it receives the message, where is the message actually heading to? So it gets the address so that it can be able to deliver the message to the right place. So if you're looking at message passing as a programmer, if you're coding using message passing, then you find that you're going to have a lot of things to do because you have to specify a lot of information. So if you're sending something, for example, it's a message you're sending, you have to specify information such as the address and who you're sending it to. So any address, any identifier, where are you actually sending this particular message? So you're using message passing to code, then you'll find that there's a lot of information a programmer will need to add. So when you're looking at message passing, apart from IP protocol sockets, there's usually also MPI, message passing interface. So there are also some programming languages which now use the message passing interface. So you can use that to be able to code. So you can also write message using this particular interface where you can now specify where you are sending your message to. So where are you sending your message, which address? So there is actually a format that has been defined using the MPI interface to be able to send and receive a message. There is also parallel virtual machine, also PVM. Also, it's also another way of using the message passing. So when you're writing your code, then you can use either of these to be able to pass your message. So these are just some of the examples. There are other ways to be able to, if you're implementing message passing as a way of communicating. Apart from message passing, there is now the distributed objects technology. So instead of now using messages, you can now communicate using the objects. So with this, you actually invoke methods. So data, you're transferring data by means of arguments, so the parameters that you pass. So that is what you're actually using to transfer the data. So you transfer the data using the parameters that you pass out. Now you're passing your arguments. So those are now what correspond to the messages. So you find that with this object, you can find that, for example, you can have a client and a server. So with a client and a server to be able to communicate, then you have to invoke a particular method. So you're invoking the particular methods to be able to communicate. So if you're using this, because we have written code in object-oriented programming, so you have written your Java code, which is C. So you know as you're writing your code, it's not like the message passing. It's not like you're using message passing to actually write your code. So if you're writing using OOP, you will not have to now say maybe specify ports like the way you do when you're using your message passing, specifying the address, the identifier. You will not specify all that. You just actually just create your method and have your arguments. So distributed objects, it was more of an easier way for people to actually write code. So instead of now the message passing way where the programmer had to know so many things, so we wanted an easier way where it had more abstraction. So with more abstraction, the programmer had to just write fewer lines of code. So they had to know less. But with message passing, a programmer really has to have a lot of information as they're writing the code as compared to the object-oriented way. So this is also a common diagram that you've seen. So if you're looking at organization of a remote object with a client-side proxy, then you find that if you're looking at the objects, there is the client side and then there is the server side. So with the client side, then you're going to have your client, then maybe it invokes a method. Within the invoking of the method, you have your proxy, which is more of a stub. So you have your proxy. Here we have our operating system. Since we are now assuming it's distributed, so there are two different machines, you will have a network. So you will have to connect these two machines. So you can connect it using any connection protocol that you can have. So there is now connecting. Then once you connect, you have your server operating systems, then you have the skeleton. So the skeleton is more of a server stub. So there's the client stub and the server stub. Then you have your interface, you have your methods, your objects. So if I may ask, what's the purpose of a client stub? You're having a client stub. What's the purpose of a client stub? Because we have, I think you've done this when you're doing your RPC and RMI, you've seen this diagram. So because you're looking at distributed objects, we're now looking at what is the common organization of a remote object. So if you have this, what's the purpose of a client stub? Conversion of parameters. What else can a client stub do? You have your client stub. You have also a server stub. What will a server stub do? Implementation of the remote interface. That's correct. So then you have your interface, you have your methods, the state, and that is now the object. So you have your client and your server. So you find the data and operations will actually be encapsulated in the object. So with the object, you have the data. Then any operations implemented as methods will be grouped into interfaces. You created interfaces when you're doing your OOP. So with OOP, you're doing something to do with interface. So you created an interface. So you know what an interface is. So operations implemented as method will be grouped into interfaces. Then object will only offer its interface to a client. So the client will only be able to communicate with an interface. Which is here. So there's an interface which is now offered to client. Within the interface, then they can be able to see there, to be able to invoke any method. Then there is object server, which is responsible for collection of objects. So you have an object server. So the server side has the objects. Then you have the clients tab. So the clients tab, also the owner, the proxy will implement an interface. As we've said, so that it will implement the interface. So because you've said the object will offer its interface to the client, and then the client tab will be the one which is implementing the particular interface. Then we also have the server skeleton. So the server skeleton is on the server side, which will handle and marshalling and object invocation. So there is the skeleton which handles any object invocation, because the client machine is now the one which is requesting. So so there is the invocation coming from that. Skeleton is the one which is handling any invocation. So this is just a recap. Apart from that, there were concepts that we learned about compile time objects and runtime objects. So with compile time objects, these are just language level objects from which proxy and skeletons are automatically generated. So those are the compile time objects. Then you have your runtime objects, which can be implemented in any language, but they will require a use of an object adapter. So we also came across object adapter that makes the implementation appear as an object. So you have the object adapter, which will make implementations appear as objects. So remember, we are now moving from message passing. We now want to communicate using the objects. Apart from that, there is a concept of transient objects and persistent objects. So with transient objects, they only exist when the server exists. So if the server is not there, so that's why they are more of a transient, more of a transition object. It only exists if the server is there. Then you have persistent objects, which are independent from the server. So the persistent objects are always there. So that's the definition of the two. We also have a servant. So if you're looking at a servant, is the actual implementation of an object. So sometimes it only contains the method implementation.
Holy shit.
Then this one, a servant can be implemented in Java or C++ as classes. So the classes can be the servant. So if you're looking at Java or C++, then you have the classes. If you're looking at C or COBOL functions, then anything to do with structs. If you're looking at this, if you're coding in these languages, there's the structs, there's the records, and it has tables. So those ones can be implemented as a servant. This is just simply an implementation of an object. So still on that. So we have looked at this, the skeleton. So I'm just reviewing the concept that you already learned in the distributed systems, concepts about the definitions of things that you'll find in objects. When you're talking about objects, what will you find? We also, so we're also looking at that one you've looked at, object adapter. So when you're looking at an object adapter, it's more of a manager of the objects. So the manager of the objects, one, it will ensure that reference object is actually activated, and it will also pass any requests to the appropriate skeleton. So if you're having a request from the client, so the object adapter will be the one which is passing the request to the appropriate skeleton. And also it will be responsible for generating any object references that you're going to have. So this is just a summary. So you have your object adapter there. So you have your stub. So you have your skeleton there. So this is just an object server. So on the server side, so you have your objects. So these are 3 objects. Then you have your object adapter. So when a request comes from the client, it goes to the server side. So it will have the object adapter, which will actually manage the objects. So it inspects the incoming requests. So as it inspects the incoming requests, that's when it ensures that reference object is activated. So any object that has been referenced, any object that is required is actually activated, and it also passes the request to an appropriate skeleton. And here is the adapter. So the requests are coming from the client side, then the adapter is now here to be able to now see. So with the objects, the objects tab, which is now the skeleton, so it will now check, am I supposed to pass this to this or this or that? So that's the work of the object adapter. Then apart from that, we had the distributor. So this, we were just looking at the definitions, what a remote object can actually have. So within a remote object, we have talked about what it can have, how messages are passed from the client to the server, and what is there, the proxy and the skeleton. So you have seen the client stub and the server stub, which is now the skeleton. Then we have also seen the object adapter and what it does. So apart from that, now the concepts of the object are now what is now used in Java and Codebus. So these were technologies that were actually put across. They're just examples of the technologies that were implementing now the distributed objects. So before RMI, there was the RPC. How was it working? Remote procedure call. How was the remote procedure call working? Remote procedure call. Anyone who can give a summary of the RPC, remote procedure call? Assuming it's now calling from the client to the server, what happens? From client to the server, RPC. Okay, what's the difference between the RPC and the RMI? Remote method invocation. Is there a difference between the RPC and the RMI? Any difference? Yes, correct.
I think for one difference, I'll say that RMI supports OOP, that is object-oriented
Yes.
programming, and RPC supports procedural.
That's very correct. Anyone else? Anyone who can give a summary of how RPC works? Summary of RPC. So just like the local procedure call, but now this procedure call is now remote. Thank you, Newton. RPC is procedural, RMI is OOP. RPC is request and response. Thank you, Aweru. RPC involves functions, while RMI is about objects. That's very true. So with RMI, it's now about the objects. So we are now more of sending objects. Then RMI is so there's also Anthony. In RMI, the server returns an object, while in RPC, the server returns a result. Also, that's very correct. So with RMI, it's more objects, and that's a result. So we are looking at now with objects. RMI is now, as we have said, object-oriented implementation of the remote procedure call model. So with RMI, it's an API for Java programs only. So using RMI, you'll find that the object server will export a remote object and register it with a directory service. As we have said, it's more of the objects. So it's moving objects. So it will export a remote object, register it with a directory service. Then you'll find that the object will provide the remote methods, which can be invoked by the client programs. So we'll find with RMI, we'll have a remote object, which will be declared with a remote interface as an extension of the Java interface. Then we'll have a remote interface, which will be implemented by the object server. Then also we'll have an object client, which will access the object. So the client will access now the objects by invoking the remote method. So you'll have now the remote methods, which will be invoked by the objects client. So the client will access it by invoking the methods associated with the object using the syntax provided by remote method invocation. So the syntax that will be provided such that the object client can be able to request for or access the particular methods. We have talked about this an object registry. So we'll find that with RMI API, it will allow a number of directory services used for registering an object. So as you've said, an object will be registered in a registry. So one of the directory service that you have for Java RMI is the RMI registry, which is provided by the Java Software Development Kit. So with the RMI registry, so this is what is used, one of the things that are used as a directory service to register our objects.
Hi, mom. Just going. I'm still in class.
So you have your objects
I'm still in
client,
class.
which will be able to register an object in the directory service. So then we still also have our stub and our skeleton because you have your object. On the client side, you have your client stub. On the server side, you have your skeleton. So Then you also have your remote reference layer, and then you have your transport layer. So that with the transport layer, now this is where the connection takes place and where information is transported. So it's more of a physical data path for transportation. So there's connect, you can connect your nodes, and it also sets up a transport protocol. So this is now more of a detailed way of our RMI, remote method invocation. So you have your objects, you have your proxy and your skeleton. So this is the server side and this is the client side. So there is now the invocation. So there is now the communication. So there is the network. So it's request for an object, then it actually gets back the results. I've actually summarized things because we have done this before, so that I am summarizing, not going to so much detail. The other thing we have under distributed objects, common object request broker architecture. Before you talk about the common object request broker architecture, there is the interface definition language. So which when you're talking about the interface definition language, you will find that this is also what the core bar actually uses to define its interfaces. So the interfaces are defined by the interface definition language, such that with this particular platform, since the RMI was specific for Java, then they wanted to find a platform which will now not be specific to one particular language, which can actually be used by a number of languages. So you'll find that now we'll have now the core bar architecture. So with the core bar architecture, before that, there's now the interface definition language. So with the interface, it will specify the API that clients can use to invoke operations on an object. So it will specify the set of operations and the parameters needed. With an interface, that's what it does. With operations and the parameters. So those interfaces that you're creating will now be defined by an interface definition language. So whenever you're creating an interface, there is the IDL to define the interface. So with IDLs, we'll find that they are declarative languages to create interfaces. So they will not specify any executable code because they don't want to be language specific. So they will not also specify the codes. So if you're looking at any middleware products such as Corba, then they'll provide interface compilers that pass the IDL description of the interface. So you're going to have the interfaces being defined by the IDLs. Then any other products can now be able to interpret the description, that is the descriptive language, interpret it and be able to read it. So with the compiler, it will produce classes which are corresponding to the proxies. So once it interprets it, then you're going to have classes for which will be for the proxy side, for the client side. So it's going to produce classes in the language of the client side. So whichever language the client side was using is going to have that. Then also on the server side, it's also going to produce skeletons which are corresponding to the language on the server side. So it's more of, it has to map. So there'll be language mappings which will be defined to allow to generate proxies and skeletons in the implementation languages of the clients and the servers, respectively. So that's the interface definition language. So that's what it will do. So then we can talk about now the common object request broker architecture, which is an architecture developed by the object management group. So with this one, it's an architecture which will specify interoperability between distributed objects on a network, because it said with distributed things, they are not the same, they're different. They have different platforms, different things. So you want a platform that can be able to ensure that the different things, the different hardware, software, etc., communicate. So for this one, it enables communications between two objects that are heterogeneous. So they are different, so two different objects. So if you're using CORBA, that is the Common Object Request Broker Architecture, then you can write it in C, C++, COBOL, or Java. I'm assuming that we wrote it in Java when you're doing OOP. Did you write this in Java? Did you use Java programming to write this? Yes, good. So this one you can write it in C, C++, COBOL, Java, if you're creating it. So if you're using this. So let's have a 10 minutes break. So 1 hour has passed. Let's have a 10 minutes break. And then you come and continue. So let's have a 10 minutes break. Two objects that are of different types, that are of heterogeneous type, and they can be written in C, C++, COBOL, or Java, which you said we wrote it in Java. Then you find that with the CORBA specification, it will be detailing how the interfaces, so it will be more providing details about the interfaces and characteristics of the object request broker. So there is the object request broker, which will be used to communicate between the objects. It will also specify functions that will allow the object to communicate. So any functions that will allow the object to communicate, CORBA will also specify.
And what is your name one more time?
So any services used by application objects will also be specified in when you're writing your when you're implementing CORBA. So if you're also looking at object interaction, when you're looking at object interaction, they usually interact through requests. So with a request will have information such as the operation to be performed, the target object, and parameters. Because you've been talking about a client sending a request to the server. So with the request, they're sending it as objects. With this particular request, it will now be it will have information about the operation, the target object, and it will also have some arguments or some parameters.
Yes, sir.
Then there's also the interface, which is still there. So with the interface, will now be more of a contract. You can call it a contract between the client and the server.
How much that would cost?
So there's also an IDL which has been defined for CORBA. So with IDL, you'll find that with the proxies and skeleton, they're usually generated through the IDL compilation. So when the IDL is compiled, then you find the proxies and the skeleton. So the language specific proxies and skeletons are actually compiled.
61 inches.
So any objects that you're writing with CORBA, they will not know any underlying implementation details. So there's an object adapter which will be mapping the generic model to the specific implementation. We had looked at the object adapter. We talked about the object adapter being more of an interface. So it's more of receiving the requests. Then if it receives the request, if the server side has several objects, for example, once the object adapter receives the request, it will now know where to actually take the request to, because you've seen with a particular object, it already has information about the target object, the operation to be performed, and any parameters. So when it gets here from the client side, when it gets to the server side, it reaches and gets the object adapter. The object adapter can actually read the request and be able to now know what to actually call or where to send it to. So which skeleton, which server skeleton will actually receive that particular object request. So this is the architecture of the callback. So this is the full architecture of the callback. We have an object request broker. So with the object request broker, it is now more of allowing communication between objects. So the object request broker, so this is what allows the communication between the objects. Then we have the interface repository. So with the interface repository, it usually provides a representation of interfaces for all the server objects. So we have been talking about an interface. We have talked about what an interface consists of and what an interface does. So this interface repository will now be providing a representation of all interfaces of the server objects. Remember, in the server side, we are just representing one object right now, but in the server side, we will not have one object. We can have so many objects in the server side. So with the objects, to be able to communicate with the objects, now we'll have to communicate or access any methods through an interface. So that's why in OOP, we were creating interfaces. So with the interfaces, now in this particular architecture, the interfaces will be placed in one particular place, which we call the interface repository. Then once they're placed in the interface repository, then you'll find that now that is what will they will all be there. That is, it will be easily accessible. So it usually corresponds to the server object IDL specification. So you've talked about the IDL interface description language and its specification. You've talked about it having it has to be passed so that depending on the programming language, it can now be written or passed and presented with the specific programming language on the server side or on the client side. Then with the clients, they can now access this repository to learn about server objects, because you've said that they will access server objects through interfaces. So they will learn the server objects that are there and the types of operations that can be invoked, because they're not just invoking operations blindly. So we can now know which type of operations can be invoked and any parameters that are accepted by the interface. So with this one, it can also be used for dynamic invocation of objects. So the dynamic invocation of objects, you can also use the interface repository, because the interface repository already has information about the server side object. So you do your dynamic invocation. Then we also have implementation repository on the server side. So this is the interface, then the implementation side. So once you have your invocation, it communicates to the object request broker, then you have your implementation repository. So with the implementation repository, it has implementation details of the objects. Remember now with the interface, it was just specifying the server objects. So it's just specifying which server objects are there and any operations that can be done and any and any operations that can be done. Now, with the implementation repository, it specifies the implementation details for the object, implementing the interfaces that are stored here. Then within that, it's also the main information is a mapping. So information about that implementation is only just a mapping from the object's name, because you'll have an object name to the file name, which implements the respective service. So it's more of now you're getting a particular service. So it's you have sent an invocation, so you have invoked a particular method. So you want it gets to the implementation repository, it checks with the object name that you have actively invoked, then it also maps to the file which implements that particular respective service that you're requesting for. Then you have your object adapter here. So the object adapter, it's now the one which gets the request. So it solves any incoming call. So it activates the right method via the skeleton, because you've said now we'll have so many methods. So with the object adapter, with your requests, it will now know which skeleton your data should be sent to. Then we have the object request broker, which is here. So the object request broker, it now allows us to be able to communicate. So the objects can now be able to easily communicate. So with the communication, we have really talked about the communication, because we just issue a request from the client side to the server side, or if you're not issuing a request, there is now the dynamic invocation interface. So instead of you issuing the request being issued, there's also it can be done dynamically. So invocation can also be done dynamically. Then when you're doing an invocation of a specific server method, so the invocation will be performed by the server skeleton, which gets the request forwarded from the object adapter, which is what we have been talking about here. From the object adapter, it forwards the request to the server skeleton.
Right now, I have no experience at all. I've actually, I have a
So that is on distributed objects. So one, we have mentioned on something on the message passing. Then we have moved to distributed objects. Before with that, the distributed objects, we have talked about the distributed objects, so it's more of way of communicating through invocation of the methods. We have had some definition, looked at the structure, how it looks like with any remote objects. So we have been defining things, more of a recap. What's an interface? What's a client tab? That is the proxy side, the server skeleton. So you have that compile time and runtime objects, transit objects, persistent objects. You've looked at what a servant is. You've said it can also, an example can be a class, a Java class or a C++ class. You've looked at now the skeleton and how it works. We have looked at the object adapter, which you've said is the manager of a set of objects. So it handles all the incoming requests. So it will inspect the incoming requests. And now once it inspects the request, it will ensure that any reference object is actually activated. So it knows where it's the invoked object is actually so it is activated. Then once it does that, it passes any request that it receives, it will pass it to the appropriate skeleton, and object adapter is also responsible for generating the object references, which you talk. So this is just object adapter when you have multiple objects, which we saw. So with the multiple objects, object adapter will actually send now forward the request to the appropriate skeleton. Then with the appropriate the skeleton will be able to continue from there. We've looked at RMI and how it works. We have talked about the difference between RMI and RPC. We already know how RPC works. So the remote procedure call. So when your caller is actually requesting for something, so we really know how the message, the procedure calls are actually working. We've talked about RMI having a registry and how it works. Then you've talked about now the callback. So these are distributed objects. These are distributed object technology. Because within the distributed objects, there are a number of technologies. You're also going to read that in the paper that we have to summarize before the next class. We're also going to have it there. So you've talked about how it works because it's under objects, which is just a technology which allows objects to communicate. So we have looked at message passing and distributed objects. So we want to look at the last two, then end the class. Also, with you can have communication. You can have event-based bus architectures. So with events, if it's more of the same whereby you can have event listeners. So you usually have an object such as container. If you're looking at Java, you can have an object such as a container implementing a listener interface. So the way that works is the same way the event-based bus architectures work. It's more of having a listener interface. So just listens, then reacts. So when you have these, usually methods in the interface which container implements usually react to events. So whereby you can have an example of on click of a button, then something happens. So this one usually is also done in Java, also with Java. You find that it's more of reacting to an event, e.g. button being clicked, menu being pulled down, activated, etc. So the code for these methods usually are in the container class. When you're doing your Java, you have your codes in the container class. And then also the final code usually in a constructor or the init method, which will register the container as a listener to certain events, such as a button being clicked, because you have to also be able to register it to now the events. We have already written code for this. So when you're looking at now, that was just an example. If you're looking at Java, how the events work. Then if you're looking at now these architectures, then it's just the same thing. So they just work the same way. So you're going to have your object bus. So this your object bus, and you have your listener objects. So the bus connects to a number of listener objects and to a transmitter object. So you'll have your listener objects and your transmitter objects, and then it will send data along the bus. So your transmitter object sends data along the bus. Then when the data appears on this particular bus, each listener object is executed to read and process the data. So that's the event bus architecture. So you can also have this particular architecture. So this, we're just showing one channel here. We can have so many channels. So transmitters, objects actually sending data, and the listener objects actually listening to the data. So they read the data and process the data. This we can have two ways of actually doing it. Okay, before we get to the two ways, that is the two ways, hub and spoke, and the other one. For this listener object to be able to actually listen, they have to register with the bus. The same way event handlers usually need to be registered when you're developing a visual interface, maybe an example of Java, then you will register your listener objects with the bus. So it is just the same concept that we have been doing with OOP. No problem, Isaac. That's okay. So you find that in the bus architecture, the listener objects will actually subscribe to a channel. So it's more of subscribing to a channel to receive objects which are dispatched along the bus. So a listener object has to register so that they can receive the objects that are being dispatched to the bus or the channel.
Different directions. So now all we gotta do is program some simple movements, and there we go.
So
It's not working.
we can talk of this as a push technology, where the data is pushing. You're not requesting for the data. With the others, it's more of client invoking the method, so it's invoking. But now this one, the server is just pushing the data. It's just pushing the data. Then you just get the particular data. So applications that mainly can be used with the event-based architecture, things like delivery of stock market data, because with the stock market data, the financial subscribers will not be requesting for it. You want it such that it's a real-time basis, so the server is just pushing things. So if the server is just pushing information, then you want an event-based bus architecture, whereby you have just subscribed to it, then any new information is just pushed to your side. If you're looking at a conferencing application where messages from conference participants have to be broadcast in real time, you also want an event-based bus architecture. If you're looking at any distributed multimedia applications such as video on demand, where large chunks of data have to be delivered to subscribers on real-time basis. So mostly if you're looking at something that is real-time, so in summary, if you want something that is real-time, then you'll want the event-based bus architecture, such that people are just subscribing to that, then data is just pushed to their side. Things like chat rooms, you will also want to use that architecture. If you're looking at event-based, then you can apply it as a hub and spoke architecture or a multicast bus architecture. So this is just a design, but it's still the same event-based bus architecture. So you have your hub, then you have your transmitter objects sending data to the particular hub object. Then from here, it can now send data to listener objects. So that instead of now transmitter object sending it to a channel, it's more of the one aligned. Then here, it's more of a central place, which is the hub object. Then the hub is now sending data to listener objects. So there is a central hub which is carrying out the transmission of data to listener objects. And then the listener responds to the event of the objects being dispatched by the hub. So it can also respond to the hub. So it needs any response, so it can respond to that. So with the event-based bus architecture, it can also be developed using technologies such as RMI or and objects. So that architecture can also be applied using that the technologies. So the advantage is that all objects can pass through a hub object, but there's also a disadvantage. It can generate large amounts of traffic because everything is on one particular. So it depends on one hub object. So if that particular hub object malfunctions, the whole system goes down. So that's the big advantage of using hub and spoke. Under event-based architecture, designing it, the hub and spoke base. So the other way is now our bus. We can now just continue with our multicast bus architecture. Where we broadcast the message to a number of receivers. So the listener, the transmitter object, we broadcast the message, the listener objects, be able to get the message. The last architecture is a tuple architecture. So this was just a project because now everybody is now trying to improve how we the distributed system, because distributed systems is still very complex, and you'll find that with most architectures that are being proposed, then you'll find that it is at first that they're still tightly coupled, because we want to have loosely coupled architectures. That's why everybody is now still coming up with architectures which can actually be applied, which we can now use in our distributed systems to distribute whatever we are distributing. So mostly one of the things is just communication, but then we want it loosely coupled. So there is now a tuple architecture which was inspired by Linda, known as Java spaces. So with Java spaces, you'll find that you'll have one or more spaces, each containing objects. So you'll have a space, then the spaces are containing the objects. So you have a distributed systems, but in now forms of spaces containing objects. So the black dots are representing objects within the space. So you have your space, object, space, object, etc. So the clients can now access the spaces. So with the clients, if they wanted something, they can allow access the spaces to be able to get. So in the figure, you find that we have the three spaces, so the three areas. Then a space is a persistent object store. So the space is just a persistent object store. So it stores the object. So because you see the dots are now the objects. So theoretically exists forever. That's why you're talking about persistent. Persistent is more of like a permanent thing. So clients can now access these spaces using three operations. There is the write, read, and tick. With write, clients can now write new objects to the space. Read, they can read contents from the space. Tick, they can read an object from the space and remove it completely from the space. So with these particular spaces, so they can use the three operations to access the objects in the space. Important points about the Java Spaces technology. One, data can be held in the space permanently. So we have talked about the persistent stores, the persistent object stores. So data can actually be held more permanently. The spaces are shared, so client objects can easily access the same space concurrently. Then also, objects stored in a space are also associative. Associative in terms of with associative, you have a key value. So usually if you're using the Java spaces, you can also use the associative lookup. So you have your key used to read, take, or write to an object stored in a space. So looking at associative, when you're doing your web programming, actually in PHP, you had your associative arrays, key value, So these spaces are associative. They have the keys, then you have your values to read. Then no problem, Marvin. The technology is also transactionally secure. So with this technology, when you're talking about transactionally secure, we say that the programmer does not have to write any complicated code to ensure that transactions are executed securely. That is, the ACID properties are actually maintained. So they are secure. So Java spaces transactions are usually supported on a single space over a number of spaces. So that is on tuple architectures. So we have seen the different ways that the different architectures that can be used in communication. Before the distributed objects, we've looked at message passing. So I just started from message passing, but in your operating system, if you're looking at your operating systems class, we looked at what a process is. Then we looked at how processes can communicate. Then you looked at now the shared memory. Then you look at the message passing. Then there's also threads. You can also there's threads, etc. So even with message passing, I really summarized it. So I can add more notes to it for those who need recap, but I really just summarized the message passing. So I will just add some few notes to it. So we have seen that there's now with the distributed computing paradigms, then you can have your message passing, how you can communicate with message passing. Then the key thing that we want to look at in this particular course is now distributed object. It's more of the object field. So with the distributed objects, you've seen what an object is. Then with the object, you've seen also the representation of objects. Within objects, we have seen the distributed technologies, the distributed objects technology. We have just looked at two, that is the RMI and the CORBA, Common Object Request Book Architecture. Then there is also another one, there is the DCOM and many more, which you're going to read also in the paper. Then apart from that, we have also looked at event-based technology, how now objects can communicate using the event-based technology, where we have your listener objects listening to the events. Then you have also your tuple-based technology, which is now not really widely used, but it's a technology and distributed systems, where you now have your spaces, the Java spaces. So that's it on the introductory class. That is now that. So in the before the next class, okay, as we conclude this, I will send the paper. Then with that, before the next class, kindly summarize. Then with the assignments that I'll be giving you, the assignments will consist of your course one. So if you miss out an assignment, I will really not follow up on you. So if you miss out an assignment, then no, it's part of your coursework marks that you've actually missed out. Because with the assignments, depending on the number of assignments, I usually sum up, like right now, since we are not in school, then with the online classes, I will give a number of assignments. Then at the end, I will now sum up the assignments. For example, if the assignments were 4, I can take the first 2 assignments and say cut 1. The next 2 assignments I say cut 2. Then we'll see if we can do a project, depending on how the semester goes. If we can do a project, we can do a project, just something small, maybe converting a legacy system into a service, implementing service-oriented architecture. So you're just converting a legacy system into a service-oriented architecture. We can see if we'll do that. So if we, for example, do a particular project, then there's also the project marks. So kindly ensure that you do every small assignment because it will just be a mark of 2 contributing towards your coursework. Do we have anything you want to say, anything you want to include? Okay, if we have nothing, okay, please, how do we check the register? Okay, with the register, you're just going to add your names after we finish. Yes, Isaac has something. Also, Rebecca has something. Yes, Isaac. Isaac.
Hi.
Hi, how
Hello.
are you?
Hi.
Hi.
I'm fine. I'm fine. Okay. So now we're having like there's one unit they forgot to add to our semester last semester that they have pushed it to this semester. So we feel like we are like our schedules are a bit very congested, bearing in mind that we have our 4th year project. So I was suggesting if we can, if yes, we have to do the project.
Okay.
It can be good if you tell us earlier so that we can even plan ourselves. Like we have 3 months to plan and know where to put where and what. But if we can agree not to have the project, it can also be a really good thing.
Oh, okay. I think as the semester goes, then we can agree to either having it or not having it. Even if it's a project, it will not be a big thing. It will be a very small thing. So
Yeah.
don't worry about that. I'll take into account all that.
Thank you so much.
Okay, thanks. Rebecca, you had something?
Yeah, I had a question. How is submitting the summary of the introductory the PDF?
Okay, how in the sense that where to submit or how in the sense that where to
Yeah.
submit?
Yes, where to submit.
Yes, so I will request Ms. Yvonne to create for me a course in the e-learning. Then once she creates, I'm going to alert Jerry and Caesar. Then they will send you the information.
All right, thank
Then you
you.
can submit it there. Okay, welcome. Okay, if we have nothing else, once you add your name to the charts, then you're free to leave so that I know how many people I'm waiting for. Just add your names to the charts so that I know how many people I'm waiting for. So leave so that I know how many have not added their names. Thank you. Also include your group so that it's easier for me to update the register.